Okay, thank you very much. I am, at this moment in Argentina, it's 10 p.m. First of all, I would like to thank the speakers for the honor to share this conference and the honor to be one of the speakers. It's really nice to share to the time with Toshiyuki Kobayashi, who has done such a deep contribution to group representations and other areas of math. The title of the talk is Another Branching Duality in Branching Law, and it's based on work in progress with Bent Orsted, work I did with Duflo and myself, and it used a lot of ideas of Kobayashi, Kobayashi-Pefner, the thesis of Nakayama, directed by Kobayashi, the work of Kobayashi-Oshima. These duality stories I learned in a paper of Ortes and Speck, and from there we start working with Orsted on the subject. And also we had conversation with Duflo on the subject. The step of the talks, don't be scared, is I will sketch the first duality formula, and then when I will start describing the ingredients in this formula, some of them you know very well, all of them, and almost at the end I will give you the final duality formula and the isomorphism involved in the formula. And if there is time, I will explain some tools that we use for the proof. So the ingredients for the formula are a symmetric pair, GH. Let's assume GH is connected. We fix a maximal compact subgroup of G, the Cartan involution is theta, and we assume from the outset that the theta commute with sigma. Let us assume that H intersection K, which we call it L, is a maximal compact subgroup of H. The other ingredient is the dual subgroup to H, which are learned in the work of Oshima and Matsuki, and since theta commute with sigma, theta sigma is an involution, we take the fixed point, that's the H naught. And it is a theorem that L is also a maximal compact subgroup of H naught. So now we fix an irreducible square integral representation for G of lowest K-type tau W, as Orsted spoke about it yesterday, and an irreducible square integral representation for H of lowest K-type sigma Z. Then inside the representation space BG, V upper G, we can compute the following. In V upper G, we compute the isotypic component corresponding to W. That's a subspace of dimension W. And as it's a K module isomorphic to W. And now we apply the universal enveloping algebra of H naught to it. That gives us a subspace included in the K finite vectors. So the first version that I'll tell you of the multiplicity formula relates the continuous homomorphism from BH into BG, the space of holographic transformations from BH into BG in the Toshi's language is isomorphic to the following. U of H naught W is a H naught L module, so we can compute the multiplicity of Z, the lowest L type of BH on it, and that's these two vector spaces are isomorphic. So the talk is to make this more precise and somewhat sketch. In order to make it precise, we will need the realization of discrete series as functions spaces or vector bundle section, and to understand much, and also we need to understand this U of H not W. Oh, I didn't say it, but we assume from the outset that the VG is an H admissible representation. Otherwise, we don't know if such a formula holds. One can write it, but we don't know if such a formula holds. So let me say that the complete list of triples GH pi, such that GH is a symmetric pair, and pi G is an irreducible square integral representation of G, which is H admissible, that's known. That has been computed by Kobayashi and Yoshiki Oshima, and by myself and Duflo. Some nice pairs that have pi GH admissible are, for example, F44, SO4, and then the H naught is symplectic 1, 2 plus SU2. I call up to this pair because we will use it for examples. Another nice example is EC2, F4, the discrete series, some discrete series of EC2 admissible to F44, and the duality is involved, the H naught is symplectic 3-1. In the papers of Oshima and Matsuki, one can find the complete list of everything. So let's give a first description of U of H naught W. Where let's recall that a reducible square integral representation has a unique lowest K type in the sense of Bogan, and is of multiplicity 1 in restriction to K of VG. This was called, when I was young, Blattner's conjecture. And the next result I like to recall is two irreducible square integral representations are equivalent if and only if the respective lowest K types are equivalent. This is due to Vaughan and Enright Wallace, as far as I know. Hence, for each irreducible representation sigma of L, there is at most one irreducible square integral representation of H having sigma C as the lowest L type. We denote our representation by H2 H sigma. Now we take the lowest K type of BG and we restrict it to L. Then we will write it as a sum of irreducible representation of L, sigma 1, sigma n, with certain multiplicity. So the theorem that we have proven with Ørsted is that under the assumption GH is symmetric pair and pi G is H admissible, then the H naught L module U of H naught W is equivalent to the underlying Harishchandra module for this family, for this sum of discrete series. So with this restrict tau 12 decompose as a sum of irreducible with multiplicities. For each irreducible, we fix a discrete series of H naught sigma I, and then we add it up as many times as the multiplicity of sigma I and tau, and now this sum is equivalent to U of H naught W closure, if you want, inside BG. Part of the conclusion is that in this case, under this hypothesis, H2 H naught sigma I is always non-zero. So to continue, I recall something that Ørsted spoke yesterday, Harishchandra parameters. Is that the big theorem of Harishchandra is for a given group, discrete series are parameterized by element of a lattice. I like to recall what we need of that. So if there is discrete series in G, there is a compact Cartan subgroup. We fix it inside K, such a T, and we can do it such a way that T intersection L is a compact Cartan subgroup of H. We are assuming that the H also has discrete series. We are assuming that. Later on, I will explain why. Both groups have admissible irreducible square integral. So we compute the rho for some system of positive roots in T, in the Cartan subgroup T, and then an element is the dual of IT is a Harishchandra parameter for G if lambda is regular and lambda plus rho is the differential of a character of T. And the big theorem of Harishchandra, is that there is a natural map from the Harishchandra parameters into this irreducible square integral representations. I will describe the map later on. Each lambda goes into its class, and the map is surjective. The class of pi g lambda is equal to the class of pi g lambda 1, if and only if there exists W in the compact Y group such that takes one Harishchandra parameter into the other. Also, there is we can write this surjective function as a bijection if we fix a system of positive roots in K, and then we consider only Harishchandra parameters dominant with respect to this system. Let me recall that the Harishchandra parameter lambda of pi g lambda, as we have defined, is the infinitesimal character. And the infinitesimal character of the lowest K type is lambda plus rho n lambda, and the highest weight is lambda plus rho n lambda minus rho K, then the rho n lambda is what it is. Now let me recall a few facts about admissible restriction. Is that the regular elements are a disjoint union of open Weyl chambers, and each element in a Weyl chamber determines a system of positive root. Then there is this theorem of Kobayashi that's quite interesting, very nice. Assume GH symmetric and pi lambda is H admissible square integral representation. Now compute the chamber where lambda lies, or the system of positive roots defined by lambda. Then for all Harishchandra parameters in this dominant with that system of positive roots C lambda, again, pi g lambda 1 is H admissible. Let me tell you a few more things about the admissible restriction. This is a result of Gross, Wallach, and Toshiyuki Kobayashi, Oshima. GH is symmetric pair, and pi lambda G is H admissible. Then restriction to H of pi G lambda is a Hilbert sum of inequivalent square integral representation for H. It's only the discrete factors are again a square integral representation for H. And with finite multiplicity, Mj. The Harishchandra parameter of the totality of the discrete factor of restriction to H of pi lambda G belong to a unique Weyl chamber in IU. When one may wonder if they live in different chambers, and no, they live in a unique chamber. In a formal way, we write Bg lambda as a sum of isotypic components. Here it should be a strict inequality. And each isotypic component also we can write it as Om H, BH mu J, BG lambda tensor, BH mu J. Then these are the multiplicities, and the B means that there exists a system CH lambda in phi lambda U and phi HU, such that alpha mu J, the Harishchandra parameters, are dominant for every J. In a note of mine, you find all the triples GH and pi G admissibles to H, and the systems GH, CH lambda, such that for parameters CG dominant, restriction to H is pi G lambda is admissible. The chamber defined where the parameters of Harishchandra parameters of the restriction live, CH lambda. Let me recall that when U is equal to T, that's a lot of cases happens. If lambda yields H admissible, then the CH lambda is nothing else than C lambda intersection phi HT. Here there is another misprint. From the tables, also one can deduce that C lambda and the systems CH lambda are either Borel-decidental, or at most they have two non-compact simple roots, and in this case, each one has multiplicity 1 in the highest root. So the parameters in G that give H admissible representations lives in very few chambers, either in the Borel-decidental chambers or on these other almost Borel-decidental chambers. Now let me say something about the duality formula and the parameter, Harishchandra parameters. So we have A, GH, the K, LT, and the H naught, and pi lambda, a discrete series for G. And assume that this discrete series is H admissible. Then from the tables, we get the system C lambda, the roots dominant with respect to lambda, and the CH lambda in phi HT, phi HU, where the parameters of the restriction, are the mu J's, are CH lambda admissible. We write the restriction to tau to L, and the lowest K type, which has this infinitesimal character, as a sum of QI's pi L mu I. And then the UH naught W, according to the theorem I stated, is the same multiplicity of discrete series for H naught of having lowest L type sigma J. Here's another misprint. This is J should be I. So they have certain Harishchandra parameter, these H naught representations have certain parameters, Harishchandra parameters, eta I. The eta I's are and the multiplicity formula gives you the following. If you take a Harishchandra parameter of G, admissible restriction, now take a Harishchandra parameter of H factor, then the multiplicity formula says that this is the same, that VL mu J plus the lowest L type of this the H mu J occurs in this sum of discrete series. So it means there is a blunted parameter of this sum of discrete, the mu J plus rho Hn is a Blander parameter of the sum of the Qi Vh or Vh naught Hi. That's what I written here in the formula below. I can improve formulas instead change Hi a little bit, and we get that the Harishchandra parameters of the irreducible factors of the restriction of Vg lambda to H are equals to the Blander parameters of this sum of this discrete series. And there is a old theorem of Schmidt that we use in the proof that the mu j plus rho nh can be computed, have this relation with the Blander parameters. But here is the important point. The consequence of the multiplicity formula, a consequence is to compute Blander Harishchandra parameters of the irreducible factor of Vg lambda, we have to compute Blander parameters of a family of discrete series of H naught et I, H naught, which are, everything can be computed. I have not been explicit, but it can be computed. Here I give you a nice example. Take E62 F44. Then for pi lambda, E62 is F44 admissible if and only if lambda is dominant with respect to the Borel, the Siebenthal chamber. In this case, the H naught is symplectic 3-1. So this is saying that the Blander parameter, the Harishchandra parameters of pi lambda restricted to F44 are up to a rho n, the Blander parameters of certain discrete series of symplectic 3-1. And for example, if you take quaternionic, the discrete series of E62, this is what I wrote here, is a quaternionic discrete series of E62, then the representation, and then tau restricted to L is irreducible in this case. And so there is Harishchandra parameters of the restriction of this quaternionic discrete series of E62 to F44 are computed from the Blander parameters of certain quaternionic discrete series of symplectic 3-1. So in particular, here is the formula. In particular, this gives that the quaternionic discrete series of E62 restricted to F44 are multiplicity 1. This is not true for other discrete series of E62 when with lambda dominant with respect to the Borel, the Siebenthal chamber. You might have multiplicity. But in this case, it's because the quaternionic discrete series of symplectic 3-1 is multiplicity free. This is computed in the paper of Gross-Wallach in Harishchandra volume. So this is how give the duality formula. Let us reduce the problem of computing Harishchandra parameters to computing Blander parameters. And the multiplicities are the same, so and Blander parameters. For example, if you take another example is SUMN, here there are more discrete series that has admissible restriction to the subgroup. Oh, I didn't write it. No, yeah, SUMP plus SUNP plus U1. Here the H naught is UM-NP plus SUP plus UR. So in this case, the Harishchandra parameters of the restriction of a discrete series whose parameter is dominant with respect to this one of these systems, CK, are computed via Blander parameters of H0. And in this case, Blander parameter of H0 and multiplicity can be computed via a computer, with a soft developed by Michel Vernet and Valdoni Silva. So let me explicit the map. This is, recall something that Bent spoke yesterday. The map that Harishchandra parameter associated a discrete series representation. You take the lambda, such that lambda plus rho is the differential of the character. You get the system. And so now you get a representation of K of infinitesimal character lambda plus rho and C lambda. This is okay because of the hypothesis lambda plus rho differential of the character of T. And then one define H2 as the sections of the bundle G cross tau W into G mod K that are eigenfunctions of the Casimir operator with a particular eigenvalue. And there is this deep theorem of Hota, Partarasi, Schmidt, and Wallach that each of these H2 G tau is irreducible, square integrable, and this family exhausts up to equivalence, the set of irreducible square representations for H. Some properties of this space that were mentioned also by Bent yesterday, I will mention other that we need to define the explicit intertwining, the explicit map of the isomorphism, is that H2 is the kernel of elliptic operator on a vector bundle. First of all, consists of real analytic functions, because the elliptic operator has analytic coefficients. Is a reproducing kernel space, that is, for each x in G, evaluation at x is a continuous linear function from H2 G tau into W. And this implies that every continuum intertwining, holographic in particular, or symmetry breaking, any of the two, T, let's say holographic in our case, because we are interested in those, T from H2 H sigma into H2 G tau is the restriction of an integral operator. Actually, it's a restriction of something that's called a Karleman operator. And this is here, I give you here why I claim that. First of all, this the kernel is a smooth function, just a smooth function. No smooth vector, a smooth function. Such that the kt dot x star w is in H2 H sigma for each x in G and W. And this means that the kt is a Karleman operator. Well, here I wrote as an integral operator, and we prove with Ørsted, this I guess was known, that the first two things, we prove that kth, now dot z, this is a function in G that belongs in principle to H2 of G tau. One can check that. But it's H smooth, that we prove. This is because it is the image of a smooth vector in H2 H sigma. But we prove with Ørsted that under the hypothesis of H admissibility of pi G lambda, then kt H dot is a smooth vector. It's much more than being H smooth. We believe that whenever this happens, so that there is a holographic, non-trivial, such that kt is a G smooth in this, like here, kth dot z in H2 G tau is a smooth vector of G, G is smooth, then the representation is H admissible, or some at least discretely decomposable. And this is another important ingredient for the duality formula. I told you that K2H dot C is an H smooth vector in H2 G tau. But if we take the identity on the E, KTE dot Z, now this is in H2 of G tau, belongs to the isotopic component of H2 H sigma. And this is inside there, we compute the Z isotopic component. The Z is the lowest L type of H2 sigma. Then the KT lives in this space. I also wrote it in is V lambda upper G, another misprint, isotopic component B mu H, and isotopic component BL mu plus rho M. This is a key point to construct the map, the duality map, this fact. KT, and this also implies that the KTH is H smooth because KTH dot Z is a left translate by H of the function KTE dot Z. So I will isomorphics first version. We have the sigma theta, the GH, the K, G theta, TL, the H naught, the dual subgroup, and a K representation of K irreducible, such that H2 of G tau is H admissible. These are the hypotheses. Then there is a fact proven either by Duflo and myself or Kobayashi that H2 of G tau is L admissible. Moreover, as Osted pointed out yesterday, the L finite vectors in H2 G tau, the subspace of L finite vectors, is equal to the subspace of K finite vectors. This is a deep result of Kobayashi. So now I recall the U of H naught W. The definition is we take H2 of G tau and compute the isotopic component of W, which is a representation of dimension W, equivalent to W, K, and we apply U of H naught to its elements. We get an H naught L submodule. And due to the fact that the H2 G tau is L admissible, for any sigma CZ in L, irreducible representation of L, this U of H naught WZ, the isotopic component, is finite dimensional. And what I proved some years ago is that this isotopic component, you compute H2 of G tau, H2 H sigma. Sigma is the lowest L type of H2 H sigma, and sigma Z. And there compute the isotopic component. This is equivalent to the Z isotopic component in U of H naught W. I don't know an explicit isomorphism of this. I know how to prove using the machine developed by Duflo and myself in the Proceeding International Journal of the Japan Academy. I promise I will write the details of that. So if you will compute the Z component, the H2H sigma isotopic component in the H2 G tau, and now inside there we compute the lowest L type of H2 sigma component, isotopic component. This is essentially an space, and this is equivalent as L modules to U, the isotopic component in U H naught W of Z. We fix an equivalence of this. And the Nakayama's thesis, this is worked out for a holomorphic discrete series, something like this. Case by case, he does it. We fix equivalence of these L modules. Then I'll tell you how to define the intertwining map, the isomorphism, excuse me. Fix the equivalence, pick up a T, an holographic operator from H to H sigma into H2. Then we can compute the kernel. Then we have the KT E dot Z lives in this big H2 G tau, H2 H sigma Z isotypic component. We apply D, and that takes this function into a function inside U of H naught W isotypic component Z. So in this way, we get a map from H2 H sigma to Om L Z U of H naught W Z. So the map is, you take T, we compute the kernel KT. Now, we look at KT of V dot. That's a function in G. We evaluate that Z in Z, so we get the function in H2 of G tau. But this function lives in these nice isotypic components, H2 G tau, H2 H sigma Z. So we can apply D to it, and we get an element in U of H naught W Z. And so you get the map, we get the map from the holographic operators H2 H sigma into H2 G tau into Om L Z U of H naught W Z. Well, when checks. And this map is bijective. The injectivity is easy. It's just that's almost the composition. Is the composition of two injective map, D and KT, because KT E dot determine the whole kernel KT by left translation, because of the equivariance of T. So the injectivity is easy. The surjectivity needs a result of mine international journal that proves that these two spaces proves the isomorphism. I stated these two spaces, the Om H H2 H sigma H2 G tau and Om Z UH naught WZ are equidimensional, and so we have an injective map between equidimensional finite dimension, equidimensional and finite dimensional vector spaces. Therefore, is surjective. I believe that when tau restricted to L is irreducible, we have a proof that's somewhat independent of the work in international journal. So in order to understand the structure of UH naught W, we have to use a map defined by Orsted yesterday. Is the restriction map. Here another misprint. H2 of G tau consists of G functions, smooth functions. Therefore, we can restrict them to H naught. So we call R naught from H2 G tau into Z infinity H naught tau, the restriction map. And this restriction map has nice properties, as we have shown with Ben Orsted. That first, that R naught of H2 G tau lands inside L2 of H naught cross tau restricted to L W. Second is L2 continuous. Now we have been able to compute the kernel of R0. The kernel of R0 is exactly the closure of UH0W orthogonal, the orthogonal subspace to the closure of UH0W. This is true for any H0, either coming from symmetric or not symmetric. It's always true. But the kernel of A0 is, so this means R0 restricted to the closure of U and H.W will be injective. And under the hypothesis for H admissibility, R0 of this closure is inside the discrete, in the L2 of H0 cross tau W, there is continuous, there is a finite sum of discrete series inside, plus a continuous sum of discrete, the principal series of H0. And we call H0 discrete the sum of all irreducible invariant H0 invariant subspace inside here. And we prove that R0 of this is inside H0 discrete if and only if restriction to H0 of pi G lambda is admissible. And the nice corollary that we are interested is this. This tells us that in the admissible case, the structure of the closure of UH0 as of the closure of UH via R0, because R0 is injective on this space, closure of UH0W is hidden in the discrete, the contribution of the discrete series in L2 of H0 cross tau restricted to LW. And what we have done is to see what's inside there. So let me recall the result of Harishchandra, that L2 of H0 cross tau restricted to L, the sum of the H0 irreducible, H0 invariant irreducible subspaces is the sum of those that some L type is in tau because of Frobenius reciprocity, plus the sum of those L types, the discrete series whose lowest L type is contained in tau. The outside and the inside. And this is a finite sum. This is a consequence of the Harishchandra-Plancherel theorem. So let me write we write tau restricted to L to sum of L irreducibles. Then we prove that R0 of this closure is exactly equivalent to this sum of discrete series. The H0, corresponding to the sigma j's with multiplicity qj's. And now the final multiplicity formula is, we just change here U of H0 W by this finite sum of discrete series. By this finite sum of discrete series. So the map is defined like this, taking holographic operator. With that guy, we compute the kernel. We evaluated that E, let the G variable run, and evaluated that fixed C. This is now in H2 of G tau. We apply the D that we had defined before. And now we apply R0, because this is in this this guy, D of KT E dot Z, is inside closure of UH not W. So we apply R naught and we might get something non-zero. And that's true. And that this is the bijection. H2, H. But the important thing for us is to prove the bijection. But the second important thing is that the relation of the Harishchandra parameters. The formula says that the Harishchandra parameters of the irreducible factor of H irreducible factors of H2 G tau are up to a shift by rho n. The Blander parameters of these sums boldface these sums of discrete series, H2 of H naught sigma j, Qj times, and sum. We can compute the inverse image of 2R naught. To the R naught D, to this big map. And this is what we are saying, is that we can recall, this formula is more explicit. Oh no, I will go down and then up. We can recall the kernel, the whole kernel, from the kernel of KT restricted to H naught. If we know the values of the kernel KT and H naught, then we know the kernel KT everywhere. Here I wrote the formula when D is the identity. This sometimes happens for the holomorphic case. Either Nakahama or myself, we have compute for which for a scalar discrete series, the D is the identity, can be taken to be the identity. So this is the, we are able to recall when D is not the identity, when appears this more complicated formula. And we can recall recover the kernel KT, but we don't have it's a pity that we don't have a proof that if we plug in here something, what we get on the other side is the kernel of an holographic operator. We don't know how to prove it without proving the duality formula, without proving this bijectivity. Maybe when tau restricted to L, we are able to do it. I have to check, we have to check details. And also appears some operators in the kernels appears as eigen functions of the operators, but I don't. To prove all of this, we need tools. And one of the tools is something that Duflo and I developed, and as follows. Take a reductive pair and any pi lambda and the C lambda, then we define a normal connected subgroup of K out of this data. If C lambda is holomorphic, we take just K1 of C lambda, the center of K. For lambda non-holomorphic, we do the following. Take the root vectors corresponding to non-compact positive roots in C lambda, bracket them, and compute the idea, those leaves in K, compute the ideal they span. K1 of C is the analytic subgroup that defined by this idea. And we prove with the flow that when there is a symmetric pair in the symmetric, pi lambda G is H admissible if and only if this normal subgroup is inside L. This let us write split up K as a product of two normal subgroups, and to study the representation of tau corresponding as outer tensor products. And we use a lot of that to prove the structure of the U of H naught W. Here I wrote some technical results we need, which I don't want to get involved. Because it's too technical, I think, for this conference. Yeah, out of these technical results, we are going to get the following. Assume that restriction to L of tau is irreducible. And the hypotheses are admissibility, GH admissible, and H admissible, and GH symmetric pair. Then the multiplicity of the restriction of L to L of tau, which is an irreducible representation, in the big pi lambda is 1. Another consequence of these technical parts is that when restriction of L to tau is irreducible, then UH naught W is H naught irreducible. Is U of H naught irreducible. And it's the Harishchandra module for this. This requires a proof also. Nakayama has somewhat proved these results in the context of a scalar holomorphic discrete series. Well, the surjectivity follows this from this formula, this technical formula that we need to read to all the technical things there too. And this formula is proven using this technique developed by Duflo of Dirac distribution and heap psi functions and right multiplicity using those tools. So finally, I'd like to thank you for your time, and also the happy birthday for Toshi.